Hello students. Today we will be exploring the relationship between grade 12 advanced functions and grade 12 calculus. These two courses are recommended to be taken together because, as you will see, many of the concepts from advanced functions carry over into calculus. The specific concept from advanced functions which we'll be exploring is instantaneous rate of change. More specifically, I'll be showing how Unit D of advanced functions' learning goal demonstrate an understanding of average and instantaneous rate of change, and determine numerically and graphically, and interpret the average rate of change of a function over a given interval and the instantaneous rate of change of a function at a given point. To demonstrate this learning goal, we'll be completing question number 2 in section 2.5 of advanced functions. This question states, for a person at rest, the function p at t equals negative 20 cos 300 degrees t plus 100 models blood pressure in millimeters of mercury at time t seconds. What is the rate of change in blood pressure at 3 seconds? Well, in this question, we'll be solving for the instantaneous rate of change at 3 seconds. We can solve for the instantaneous rate of change by using the rate of change formula. We can estimate the instantaneous rate of change by plugging in two numbers which are very close to 3 seconds. In this case, I used 3.01 seconds and 2.99 seconds. I plug in my y2 and y1 that I found by using those x values and plugging them into the formula and solve for the instantaneous rate of change. I get a rate of change equal to 0 millimeters of mercury per second. Therefore, at t equals 3 seconds, the rate of change is 0 millimeters of mercury per second. If we look at a graph of this function, we can also see that this is the maximum for this function, as when we get a slope of 0, this means it is either a maximum point or a minimum point. When we look at the graph, we can confirm this. I plug in the function to my GDC and graph. When I draw a tangent line at the point t equals 3 seconds, I get a horizontal line, proving that the instantaneous rate of change is 0 millimeters of mercury per second, and that this point is a maximum. The fact that if the slope equals 0 is either a maximum or minimum will become very important when we move on to calculus. To look at how this concept applies in calculus, we can take a look at example 2 in 3.4. The question states that a railway company offers trips at $120 per person for tour groups of up to 100 people. If the size of the group is greater than 100, the company will reduce the price of each ticket by 50 cents for each person over 100. What size would produce the greatest revenue? We will let x equal the number of people over 100. Then we can set our domain. We know that x needs to be between 0 and 240 people. If x is greater than 240, then the price of the tickets will be negative, so it can't be higher than 240. Revenue is equal to the price times the number of people, and we can use this to generate an equation. The price will be equal to 120 minus 0.5x, because for each person, the price becomes 50 cents lower. The amount of people will be equal to 100 plus x. Doing the math, this gives us an equation for revenue equal to 12,000 plus 70x minus 0.5x squared. We next need to take the derivative of this equation. Taking the derivative gives us a formula which will allow us to take the slope of any point. Taking the derivative, we get negative x plus 70. Here is where our knowledge from advanced functions come in. Well, we know that if the instantaneous rate of a change at a point is 0, this will mean that it is either a minimum or a maximum. We set the derivative to 0 and solve for x. This gives us an answer of x equals 70. This means that taking 170 people on the trip will produce the greatest revenue. We can double check this by doing an analysis. At x equals 0, the revenue is $12,000. At x equals 240, the revenue is $0. And at x equals 70, the revenue is $14,450. This shows that taking 170 people will produce the maximum revenue. We can take a look at the graph as well to prove this. I plug in my revenue function into my GDC and graph. I take the value of the function at 70, and it is $14,450. I draw a tangent at x equals 70, and I see that it is a horizontal line, and we can see that this means that it is our maximum point. I can also take the derivative and plug into my GDC. When I graph this, I take the value of x at 70, and we see that the value is 0, meaning that at x equals 70, the slope is 0. In conclusion, we can see that the concepts learned in advanced functions carry over extremely well to calculus. This is just one example of many, and I invite you to try and explore some more examples.